The purpose of this title slide is to tell you that this is joint work with two of my colleagues, actually from the United States, and also to show you my contact. I know that the theme of this symposium is how to use AI in statistics, and actually my talk is in the other way around, is how to help AI to provide answer to statistical questions. So these are tools that the AI can use to provide answers to statistical questions. The topic that I'll talk about is to give you a very brief introduction, and then I'll talk briefly about the parallel coordinate plots, just for those of you who are not familiar with that. And then we'll talk about the problem of cluttering and how to solve it using what we call enveloping, and that will lead us to the proposed solution to the cluttering problem, which is called the space transformed visualization plot. And then I give you plenty of examples as much as the time permits. So in nowadays, the advancement of computer technology and communication technology gave rise to the availability of huge data sets, and these data sets sometimes even available in your handheld devices. So we have a data set, huge. We call it X, just the notation, which has N objects or cases or observations, on P attributes or features or variables, as different people call them, when N and or P are very large. And we wish to visualize and understand the structure and the patterns of point on the p-dimensional space. And what we have here that have no information about the existing patterns or structure is given beforehand. So this is fall under the class of what computer scientists call unsupervised learning. Data sets come in varying sizes, and what we can call big data actually start perhaps from this line on. And the big data, the availability of big data is a good thing, but also it presents us, a statistician and computer scientist, with some challenges. The first one is if we try to do statistical inference, when N is large, is very large, everything will be significant, even if it is not. We can detect the slightest difference easily, so therefore the null hypothesis will always be rejected, no matter what, when we have very, very large N. The second one is the speed. So if you ask for a plot, for example, you might have to wait for very long until you actually see the spot displayed on your screen. And the third challenge, which is called cluttering, and this is the one that I'm going to address today. So for example, if we have just two variables, X and Y, and if we want to know if they're related, so we do, of course, a scatter plot. So you can see here that when we have N equal to 100 observations, you can clearly see that the data points show a positive trend, positively correlated variables. But if you have a larger data set, I wouldn't quote even big data, of 1 million observations, that's not a big data at all. What you can see here is that it's like you put some ink on a page, and you will not be able to see any clear structure. And you get this graph here on the right after waiting some time in front of the screen. So this is the problem which I refer to as cluttering. So we have a lot of points are plotted on top of each other and next to each other, to the point that we will not be able to determine a structure or pattern from these graphs. Okay. So the problem becomes impossible when we have higher dimension. This is only 2-dimensional, y plus x, but if p, the number of dimensions in the multivariate data increases, this becomes very problematic, because we will not be able to to draw scatter plot in more than 3 dimensions. So instead of using perpendicular set of axes dimensions, we are going to use the parallel coordinate plots. I will go over introduction of the PCB very quickly, just in case, for the sake of those of you who are not familiar with it. So every axis or every variable here is drawn on horizontal line or vertical line. So in this case here we have 4 variables, x1, x2, x3, and x4. Each one is plotted horizontally, and the point on each variable are plotted on this axis here. So this is the minimum for x1, this is the max for x2, and so on. So after we do that, we connect each observation from variable 1 to the corresponding observation in variable 2, and so on. So you get this graph here, and this is what we call parallel coordinate plot. Some people, they call it the spaghetti plot because of the complication of the line crossing and things like that. Of course, if you have many observations, this plot also suffer from the cluttering problem. The PCP suffer from the cluttering problem. As an example, well, before I go to the example, so let us look at the interpretation. How do you interpret these lines that connects one point from one axis to the corresponding point on the other axis? So what you can see here, if you see what people call pencil, it means that the variables are negatively correlated. A low value from here corresponds to a high value from here, and vice versa. So this tells you that the two variables are negatively correlated, and also that we have 2 classes of the data. Each one of them, x and y, is are negatively correlated, but there are 2 different classes, as you can see. So this graph suggests that we have 2 clusters in our data where the variables are also negatively correlated. Sometimes we replace these straight lines connection by a smooth curve where the curve meets the axis on a perpendicular angle here and here. So they will be smooth and they look nicer, so to speak, than the other, but both of them are actually equivalent. So these are some references for the PCP. And the advantage here is that we can draw theoretically any number of axes, but practically up to 20 axes as long as the page will take. So we can see the data in up to 20 dimensions. The disadvantage of the PCP is that there is no natural ordering of the axes, x1, x2, x3, or we take any permutation of them. So each permutation, the graph will look different. So it is difficult to interpret, especially for large N, due to the cluttering problem. So let me just give you an example of that, which again is large but not really big data. This is the measurement of concrete structures. So we have this multivariate data here. And if you look at the PCP, it looks like that. So 1, 2, 3, 4, we have 5 variables in this case. But as you can see here, we suffer this parallel coordinate plot, just like the orthogonal coordinate plots also suffer from cluttering. These are some references here about the cluttering problem. And let me just give you an example here to illustrate the point. Suppose that we have 3-dimensional data set, and the data set has 2 clusters between x and y. If you look at x and y, you can see one is negatively correlated, and the other cluster, y and x, are positively correlated. Here they both are negatively correlated, and here the opposite. So this is what we call the plot matrix here. So that structure, because we have only 3 variables, and also we have 200 points in each. It's not many. So if we take this here and then do the PCP, the parallel coordinate plus, this is what we see. The 3 variables are here, and you can see here that we have again 2 classes between z and y. this class here to the left are are positively correlated because the line do not cross, but the class to the right, the blue class, the line crosses, so this is negatively correlated, and the relationship between y and x is similarly obtained. And we can see that we have two classes in this three dimension here, and actually the variable y by itself can be used to separate these classes. However, if we use only y, we can see there are some gaps here that may lead us to different conclusions. So this is the quick introduction of the parallel coordinate plot, and some people they try to use different tools to try to make sense out of the plots. So you have saturation brushing, you have binning, buckling, you have enveloping, and you have the proposed space transformed visualization plot. I will talk a little bit about enveloping, and then I go directly to the proposed method, which is enveloping. So these are the references on enveloping. So what is the enveloping here? Instead of plotting the entire data, we plot the data within certain values. So for example, we can say that we plot only the minimum and the maximum of each variable, but not the data in between, or the quartiles, Q1 versus Q3, and or without the data in between, or what we call concentration intervals, which are very similar to confidence interval, but they are not confidence intervals. So we look here as examples that this is the entire data here. If we plot only the minimum and the maximum, so for variable z, this is the minimum here, and the maximum is here. For one class, for other class, this is the minimum, and this is the maximum. So when they overlap, as you can see, they get different colors. So the min-max envelope does not maintain the structure on the original data. In other words, it's not clear how many classes are there, even though, again, that variable y has separation here between the two classes. So the min-max does not maintain the original structure. The Q1, Q3 PCP show you a little bit more about the structure of the data. And this is all the variables, all the observations within the Q1 and the Q3. But this, when we plot them in terms of enveloping, just show only the Q1 and the Q3 for variable 1, Q1 and Q3 for the class 2, and so on. So what you can see here is that you can see some structure in the data. The concentration intervals, it looks very much like a confidence interval for each variable, because you take the mean of each variable plus or minus a value. Usually it is a critical value times the standard deviation of that variable. But here it's not really a critical value. We just simply take values and we increase them, okay? And then we see how the plot look as a function of this C. So we have seen that the plotting of the data points within an envelope does not maintain the geometry presented on the data. So we want to look at something that will preserve this geometry. And what we're going to do here is that instead of calculating the summary statistics on the original data, we do the transformation first, and then we compute the summary statistics on the transformed data. So as an example of this here, suppose that we have a scatter plot of four points here, as you can see. And there are 4 boundary points. There are points, and this is the convex hull of all the points, but there are points inside. So these points are the boundary points only. If we do the parallel coordinate plot, okay, so you can take this is the red point with this point here is this one, okay, and the yellow point is here and so on. You can see here that this point here, which is a boundary point on the scatter plot of y versus x, it is not in the boundary point, it is in the middle point, because this point here outside it. So this point here is an interior on the PCP. So that's why the PCB does not maintain the geometry of the data. So what we do here is that we compute the PCB first, and then we compute the statistics on the transformed variable. So one problem here is that if you have two variables here, you can see that the position of the minimum on the first value does not, in the first variable, does not correspond to the position of the minimum on the second. So actually, so the minimum here correspond to the maximum here corresponds to the minimum, and the maximum corresponds to the minimum. So the geometry are not maintained. So what we are going to propose here is that we compute the summary statistics after we do the transformation, not before, because if we do that, then we keep the geometry. This is the way we are going to plot the data. So we have a function, smooth function rho of t for some value in an interval from ta to tb, and we take a linear function of the two variables, x1 and x2, with phi1 of t and phi2 of t, and we vary t from ta to tb. We can write that in matrix notation easily and neatly by having the phi of ta will be 1 and 0 because a is the minimum. So it will be 1, 0 here, 1 and 0. T of b will be the opposite. And rho of t will be, rho of t in this case here, will be at ta will be x1 only because it will be 0 for the others. And rho of tb is equal to x2 only. But of course, if t is between a and b, then we have a linear function of here. So rho of p can be written simply as x, which is the data matrix that we have, times the vector of the smooth transformation. And so this is what we have. And then what we do here is that we take each smooth transformation and take the average of the smooth value at each value of t, and we add and subtract c times the standard deviation of this smooth value, which we will know that this will be the function transpose times s times phi, which is the S is the covariance matrix of X. And then we compute that transformation for different value of C. So for example, like 3 or 0 or 0.62, the 0.3, the 3.0 corresponds to the min-max enveloping. This here, when you have C0, you talk only about the centroid, X bar or rho bar. But C of 0.67, assuming normality here, it means that is the Q1 and the Q3 here. So let me skip here for the sake of time and go directly to examples. So we have seen this example before. So this is all the data points are there. This is the minimax. Okay, if we translate it from here to here. But this is the minimax. If we take this one here, we translate it, and then we compute the minimum and maximum on a transformed data. So that structure here, which is also minimax, is the structure of the data here are kept. So you can see the similarity between this and this here. Now, if you go to take other values of C, so you get different structure here. So as C gets smaller and smaller, you can see that the structure becomes clearer and clearer. Here is another example of a data set that has 19 variables and 7 classes. Each class has 330 observations. These are publicly available data set. It's called the segmentation data. If you draw the parallel coordinate plot, you can see here that the original one, the minimax, you don't see 7 classes there. You might see 1 or 2 classes. the Q1 and the Q3 on the SCTVP plot, you can see more classes. But also you can see here that variable 3, 4, 5, 6, 7, 8, and 9 actually do not contribute to the classification. So if you're doing clustering, for example, these variables are not really needed. So you can use the graph for dimensional reduction if you wish. So this Q1, Q3, but if you go smaller value for the concentration ellipsis, concentration intervals, excuse me. And so for C equal to 2.0, this is the result. For C 1.5, for C equal to 1, so as you decrease C, you can see the separation becomes clearer and clearer in the PCP plot. So here, for example, you can see in this graph to the right, you can see that this class is very widely separated from this class, but this class is separated from this class, but not as widely as this one here. If you decrease C further, you can see actually the 7 classes if you take only the centroid of the smooth function. So each class is represented only by one observation, which is the mean of the smooth function here, and you can see the separation very clearly. So this is for the DAS data set, and I have 2 minutes left, I guess. Here is another data set which consists of 13 variables, 178 observations, and the 3 classes. If you look at these graphs here, or these graphs here, or these graphs here, you can see the 3 classes very clearly visible. So this is what proposing here to deal with the cluttering of data when you use big data, which simply said that you first do the transformation, the phi of t, and then after you do the transformation, you compute the statistics on the phi, on the row of phi, not on X itself, and then you plot it using the concentration intervals, and as you decrease C, you will get the separation more clearly. I'm going to stop here, and I thank you very much for listening, and I'm sorry about the technical problem at the beginning.